We have now a formula for the force of buoyancy on object O in fluid F, where this is the density of that fluid and this is the volume of that object. We know the force is always going to be upwards, and we wonder, when is it significant? When do we have to take buoyancy into account? Buoyancy is going to be significant on objects that are mostly gas, like balloons or other inflatables, whose density is comparable to the density of the surrounding air. But for solid bodies, the force of buoyancy on them in air is generally negligible, since their densities are so very much greater, thousands of times greater than the densities of air. We can generally ignore buoyancy on solid objects in air. But on solid objects in liquids, the force of buoyancy tends to be significant enough that we can't ignore it, since the densities of solids are not that much different than the densities of liquids. So let's consider here 4 equal mass objects released from rest in air and in water. All right, in this picture, I have a z-axis marked out in meters, and then on the right, the pressure of the surrounding fluid increasing downward, increasing here in air by about 1/10,000th of an atmosphere per meter. But then once we hit this body of water underneath, the density increases by about 1/10 of an atmosphere per meter. And we have 4 objects with the same mass, but slightly different volumes here, since they have different densities. So a wooden block and a cube-shaped fish and a cube of water that we somehow drop from rest up here in the air, and then here a cube-shaped stone block. If we make them all equal mass, then here's the free body diagram for each one of those. All have the same exact force of gravity on them. The buoyant force upwards on each one of these when we release it from the surrounding air would be negligibly small, since their densities are 1,000 times or more greater than the density of the surrounding air. So we could add a tiny little buoyancy force upwards onto each of these FBDs, but it would be negligibly small. We'll just neglect it here. So then, if the only considerable force acting on each one is gravity, then these will basically be in free fall when we release them. So these pink arrows represent the free fall acceleration, negative little g. But now, if we release those same 4 objects in water, immersed in water, and we let them go here, then these will be their FBDs. Equal forces of gravity on each one, but different buoyant forces based on their different volumes. This cube here, the wood block, the volume of water that it's displacing has a weight that is greater than the weight of the cube itself. Hence, the upward buoyant force on the cube will be greater than its own weight. It will have a net force upwards and will accelerate upwards when released. A fish, it can adjust its own density to match that of the surrounding water, so that the water it displaces has a weight equal to the weight of the fish itself. Hence, the fish can be neutrally buoyant and not accelerate when we release it. Likewise, this cube of water surrounded by water will be neutrally buoyant and balanced when we sort of place it there. And the stone block, it displaces a volume of water that has a weight quite a bit less than the weight of the stone block itself. So the buoyant force upwards on that stone block, less than the weight of the block, but not negligible. So the net force on that block will be downwards, and it will accelerate downwards, but not as rapidly as the same stone block released in air up above here. Let's now compute the accelerations of these objects by applying Newton's second law. So the acceleration in the z direction, net force in the z direction on each object over the mass of the object. So that'll be the upward buoyant force minus the weight of the object. Here's our formula for that upward buoyant force on each object, and we'll replace the volume of the object with the mass of the object over the mean density, rho naught, of the object. Rearranging this expression to get this, we see we have an mg term and an mg term that we can factor out. Factoring that out gives us this result, and we have the mass of the object canceling the mass of the object. And thus we write that the acceleration of the object will depend on this expression here. We see it's the density or the ratio of the density of the surrounding fluid to the density of the object that will determine whether we get a positive acceleration and negative acceleration that is upwards or downwards or none at all. So for the fish and for the block of water, if their mean densities match the density of the surrounding fluid, that is, if this ratio here is 1, then 1 minus 1 is 0, and they do not accelerate when released. If we're talking about our solids up here and a liquid up here in the surrounding air, well, for them, this term here is going to be approximately 0 if the density of your object is much, much greater than the density of the fluid. So this just becomes 0 minus 1, or negative little g, for the acceleration of these objects here. And we recognize they're in free fall as usual. We can safely neglect that buoyant force on them. Let's back that up a bit. What about for the two interesting cases, the wood block in water and the stone block in water? To put some numbers to it, suppose that our wood block has a density that is 3/4 the density of the surrounding water. So we put in 3/4 of the fluid density in here for the density of the object. So then density of the water cancels density of the water. 1 over 3/4 is 4/3 minus 1 gives us plus 1/3 little g. Hence, our wood block will accelerate upwards with an acceleration initially equal to 1/3 the acceleration of gravity. Our stone block, if it is 3 times more dense than water, then we sub in 3 times the density of water in here. That gives us this. Density of water cancels the density of water, and 1/3 minus 1 is negative 2/3 g. So our stone block accelerates downwards with an acceleration negative 2/3 little g. So plus 1/3 and negative 2/3 I've represented with these pink arrows here. Wood block accelerates upwards with 1/3 the acceleration of these free-falling objects, and our stone block accelerates downwards with an acceleration 2/3 of the acceleration of these free-falling objects. Okay. Let's change up the scenario here. I'm going to ask you in a moment to determine what changes will occur if we replace these 4 equal mass objects with 4 equal volume objects instead. So replace the wood block with a smaller wood block and replace the stone block with a larger stone block. We can keep the fish and the water block the same. So now they have different masses but the same volumes. So I'll ask you to pause the video in a moment and determine how the free body diagrams and the acceleration vectors in the diagrams above are going to change, and what would the new accelerations be for each of the 4 objects if they're now equal volume instead of being equal mass. So in this picture here, determine how these free body diagrams change, how these FBDs change, what the new accelerations are going to be, that is, the new accelerations here, and how these acceleration vectors would change. Okay, pause the video and consider all those effects. Ready? Got it all figured out? Here we go. Okay. So now, 4 equal volume objects released from rest in air and in water. So here they are released in air. They now have different weights each, since they're now different masses. The wood block is the least massive and the stone block is the most massive. So 4 different forces of gravity here. Still negligible buoyant forces upwards on them. So we can still neglect buoyancy on these objects in air and expect that they will each still be in free fall. So not much has changed for them. If we release them in the water, though, now we have different forces of gravity, but since they each have the same volume, they're each displacing the same volume of water, so the buoyant force on them is the weight of that volume of water displaced, so it would be the same buoyant force on all 4. Same buoyant forces now, but different forces of gravity. Still, the buoyant force upwards on this cube is going to be greater than its weight, since the water displaced by the cube weighs more than the cube itself, this wood cube, so it's a net force upwards. We still expect this cube to accelerate upwards. The fish and the water block are still in equilibrium. The stone block now is displacing more water than before, so there's a bigger buoyant force on it than before, but its own weight is so much greater than before that the net force on that stone cube is still downwards. It's still going to be accelerating downwards. So if we test our formula for their accelerations, we derived this before, we see that it depends only on the densities. The masses and volumes of the objects don't appear here explicitly. So since the densities of the big wood block and small wood block are the same, and the densities of the big stone block and small stone block are the same, then the small and big wood blocks are going to have the same acceleration, and the small and big stone blocks are going to have the same acceleration. It depends on density only, not mass or volume individually. One final note here. Drag force is a totally separate phenomenon from buoyancy. Air drag and fluid drag, these are effects that only appear when an object is moving relative to the fluid medium. So drag will start to play a role once these objects begin to actually move. Here at the moment, if we release them from rest, no drag yet, but a moment into the future, there will be drag on them, and we'll have to start taking that into account. And that drag force generally does depend on size and shape. So whereas buoyancy treats all wood blocks the same way, the drag force on them will depend on the size of the wood block.